7.4 Lesson 3, Finding Arc Length, Objectives 1. You will understand the development of the definition of the area of a surface of revolution, and 2. You'll be able to use the definition of the area of a surface of revolution to find the area of a surface of revolution. Vocabulary: frustum of a right circular cone and surface of revolution. So what is a surface of revolution? Here we define it. So we begin with the graph of a continuous function, and we revolve this graph about an axis of revolution. And what will result is called a surface of revolution. So let's look at a figure for this. So what do you begin with? You begin with the graph of a continuous function. So here is the graph of a continuous function on the interval from x is equal to a to x is equal to b. What do we do with this graph? We revolve it about an axis of revolution. So in our figure, the axis of revolution is the x-axis. So we revolve it about our axis of revolution. And what results is a surface of revolution, as you see here. So the question that we have is, how can we find the area of this surface of revolution? It's a problem because the curve is not a line segment. If it were a line segment, there's actually a formula in geometry that would allow us to find the area of the surface of revolution, as you will see with the next figure. So going back to the definition of a surface of revolution, if the graph of a continuous function, so suppose the graph of the continuous function is just a line segment. So if you have a line segment that is revolved about an axis of revolution, so here's the axis of revolution, the x-axis, and then you revolve that about this axis of revolution, the resulting surface is a surface of revolution. Now, if the original graph is a line segment, you get what we call a frustum of a right circular cone. And if you wanted to find the area of this particular surface of revolution, you don't need calculus. There is a pre-calculus formula that will tell you the area of this surface of revolution. The surface area of this frustum of a right circular cone is given by 2 pi r times L. Now, L is the length of the line segment that is being revolved about the axis of revolution. So L represents the length of this line segment. 2 pi is a constant, and R is the average of the smaller and the larger radii. So the smaller radius is r sub 1, the larger radius is r sub 2, and if you take the average of those two, you get lowercase r. So that's the formula for finding the area of a frustum of a right circular cone. This is a pre-calculus formula. In Objective 1, we would like to understand the development of the definition of the area of a surface of revolution. And in Objective 2, we'd like to use our integration formula to do some problems from calculus. For Objective 1, you start with the pre-calculus formula for the lateral surface area of a frustum of a right circular cone. And that will help you to come up with an approximation for the area, the surface area of a surface of revolution for that is generated by revolving a curve about an axis of revolution, as you see in this figure. And then after you have an approximation for the surface area, you would like to make your approximation better, and then you would introduce the limit process, taking the limit of a Riemann sum, and by definition that will result in a definite integral. So we'll read through these paragraphs from our textbook to understand the development of the definition of the area of a surface of revolution. Suppose the graph of a function f having a continuous derivative on the interval from a to b is revolved about the x-axis to form a surface of revolution as shown in the figure. Let delta be a partition of the closed interval from a to b with subintervals of width delta x sub I. Then the line segment of length delta L sub I is given by the distance formula. Then the line segment of length, the length of this line segment, which we are going to use to approximate our curve, is given by the distance formula. So the idea is this. You have a curve, as you see in the first figure, and you want to revolve that curve to get a surface of revolution. And the problem is we want to know what the surface area of this surface of revolution is. But it's not something that we can do because we don't really have a formula for it. So what we're going to do is we're going to use what we do know, which is the formula for the lateral surface area of a frustum of a right circular cone to help us with this problem. We will approximate the area of this surface of revolution by using the formula that we know from geometry. But to apply that, what we have to do is we have to say, okay, let's begin by approximating our curve with a number of line segments. Like, for example, you could have one line segment here. You could have a second line segment here. You could have a third line segment here. And when you revolve each one of these individual line segments, what do you get? You would get a frustum of a right circular cone. And you know how to find the lateral surface area of such a figure or such an object. As you can see from my sketch here, if you revolve each of those individual line segments, you will get a frustum of a right circular cone, and you have a formula that would give you the area, the lateral surface area of each of these three frustums. And if you add the lateral surface areas of the three frustums of right circular cones, then you will get an approximation for the surface area that is obtained by taking the continuous curve and revolving it about the axis of revolution. So we would like to write a sum for the sum of the areas of these lateral surface areas of frustums of right circular cones, and we'd like to manipulate our sum to get a Riemann sum, and then we'd like to take the limit of that Riemann sum as the norm of the partition approaches 0, and that limit, if it exists, will give us a definite integral, which will be the definition of the area of a surface of revolution. So continuing to read, the line segment of length delta L sub I, given by the distance formula, when you revolve that line segment, you get a frustum of a cone. And it says here, let R sub I be the average radius of this frustum. Why do we need that? We need that because in the pre-calculus formula, we have the lateral surface area of a frustum of a right circular cone is given by 2 pi, which is a constant, times r, and r is what we're talking about here. It is the average of the smaller and the larger radii of the frustum. So that's why we say here, let r sub I be the average radius of the ith frustum. So this would be I is equal to 1. Here we would have I is equal to 2. And here we would have I is equal to 3 for our 3 frustums. So R sub I represents the average radius of the ith frustum. By the intermediate value theorem, because our function f is continuous, we know suppose the graph of f, and f has a continuous derivative, which means the function f is differentiable on the interval from a to b and therefore continuous on the interval from a to b. By the intermediate value theorem, which is applicable because our function f is continuous on the closed interval from a to b, and therefore it will be continuous on any subinterval of a to b, a point d sub I exists in the ith subinterval such that r sub I, which is the average radius of the frustum, is equal to our function evaluated at d sub I. Why do we use the intermediate value theorem to reach this particular conclusion? The intermediate value theorem states if a function is continuous on the closed interval from a to b, and k is any number between f of a and f of b, then there is at least one number c on the interval of x values from a to b such that the function evaluated at c will be equal to k. So in our particular case, we know that the average of the smaller and the larger radii will be between the smaller and the larger radii. Like, for example, if you take the average height of someone who's 5 feet tall and someone else who's 6 feet tall, the average height for these two people will be 5 feet 6 inches, which is, of course, between 5 feet and 6 feet. So we're basically saying because the average radius of the smaller and the larger radii is between the smaller and the larger radii, and because we know the function f is continuous on the ith subinterval, by the intermediate value theorem, if you evaluate the function at a particular value from that interval, the output value from the function will be equal to the average radius. That's basically what we're saying. So now we're able to do the following. The lateral surface area of the ith frustum, and we have 3 frustums in our diagram over here. So now we're saying the lateral surface area of the ith frustum is given by this formula. 2 pi, but remember what r is. It's the average of the smaller and the larger radii of the frustum. And we're saying by the intermediate value theorem, there is a particular x value from the ith subinterval, so that if you evaluate the function at that x value, it will be exactly equal to the average of the 2 radii. So we're able to make this substitution for r sub I with f of d sub I using the intermediate value theorem. And of course, what is delta L sub I? It is the length of the line segment that is approximating our continuous curve, and that is given by the distance formula. And what you see here is exactly what you saw in the previous lesson when we went over the development of the definition of arc length. Everything is the same. We do the same algebraic manipulation that we saw in that lesson to go from this line to this line here. And then you'll see the same thing that we saw in that lesson about using the mean value theorem, and we use it for the same purpose. We use the mean value theorem to make a substitution for this quantity with f prime of c sub I, just like we saw in the previous lesson. And it is required that the function f have a continuous derivative so that the mean value theorem would be applicable, as we discussed in the previous lesson. So that the mean value theorem would be applicable on any subinterval of the closed interval from a to b. And this is what the mean value theorem states. And this is just delta y sub I, and this is just delta x sub I. So we're able to replace delta y sub I divided by delta x sub I with f prime of c sub I. So now we're able to replace this quantity with f prime of c sub I. So what we have here is a formula that tells us the lateral surface area of the ith frustum, which we're using to approximate a portion of our surface of revolution. For example, when you go back to our diagram, here we have 3 frustums of right circular cones, and each one of these frustums approximates a portion of our surface of revolution whose area we're trying to find. So you have to apply this formula in the case of our diagram 3 times to find the lateral surface area of each of those 3 frustums of right circular cones. And when you add the 3 areas together, you would get an approximation for the area of this surface of revolution that you obtain by taking your continuous curve and revolving it about the axis of revolution. In our approximation, we approximate our continuous curve with a number of line segments and revolve each of those line segments. That's what we're doing. So what that gives us is a Riemann sum. This is a Riemann sum. It is a sum of a product. You have this product here, and importantly, one of these factors is delta x sub I. And now what are we going to do? It states here, it can be shown that the limit of the right side as the norm of the partition approaches 0, meaning the width of the largest subinterval is approaching 0, which means the number of subintervals is approaching infinity. So we're considering what happens as we have more and more and more frustums of right circular cones where the width of each subinterval is approaching 0. Then you're going to have better and better and better approximation. So as you have more and more and more frustums of right circular cones, your approximation will become better and better and better. And if you take the limit of this Riemann sum as the norm of the partition approaches 0, by the definition of a definite integral, what you have here is a definite integral. But how do you know that the limit will exist? Because continuity implies integrability. And we know that the function f is continuously differentiable. In other words, f prime is continuous on the interval from a to b. And therefore, the square of f prime as well as 1 plus the square of f prime and the square root of 1 plus the square of f prime also multiplied by f of d sub I, this will be continuous on the interval, on the ith subinterval of a to b. So we know that this is the limit will exist because continuity implies integrability, and by the definition of a definite integral, this limit, when you take the limit of this Riemann sum, you get this definite integral. Again, this is what you learned in Calculus AB, that a definite integral is the limit of a Riemann sum as the norm of the partition approaches 0. And then it states here, in a similar manner, if the graph of f is revolved about the y-axis, what's the only difference? Well, the only difference is that now this particular part is going to be different because that is coming from f of d sub I, which is supposed to be the average of the radii, the smaller and the larger radii. And therefore, if you're revolving about the x-axis, as we have for the first case, the distance from the axis of revolution, shown here in green, to a point on the curve, that would be given by the function evaluated at whatever x is. And that would be the average of the 2 radii for the ith frustum, where you have the smaller radius here, and you have the larger radius here. On the other hand, if you have revolution about the y-axis, what happens? So let's say you have this curve, and maybe you want to revolve it about the y-axis. So this would be, for example, a particular line segment. So if the axis of revolution is the y-axis, this would be the smaller radius, this would be the larger radius, and the average of the two radii will be somewhere in the middle, and you can find that average, and that average will be equal to the distance from the axis of revolution, the y-axis, to some particular point on the curve. So I may have to adjust my diagram a little bit to make it work out, but that distance would be the average radius. If the axis of revolution is the y-axis, it would simply be just the distance from the y-axis to a point on the curve, which would be just the x-coordinate of that point. On the other hand, if the axis of revolution is the x-axis, the distance from the axis of revolution to a point on the curve would be given by the y-coordinate of that point. So that's the only difference that we have between those two situations. So it says here, in both formulas for the surface area, you can regard the products 2 pi f of x and 2 pi x. This is just a way for you to remember it. And you can read this on your own, and we'll go ahead and now take a look at what we end up with, which is the definition of the area of a surface of revolution. So now we'll go over this definition of the area of a surface of revolution, and we have a couple of figures to help us understand this definition, and of course we saw where it came from. And one thing that you'll notice is this. You'll notice that in the definition of the area of a surface of revolution, you have this part in the integrand, and you saw that with arc length. And the reason why we have that is because of what we observed in the development of this definition, where we began with a line segment to approximate our continuous curve, and then we revolve that line segment to get a frustum of a right circular cone. And of course, in the development of the definition of arc length, we also used line segments, and they were used to approximate the length of the arc by using several line segments. And because of that commonality in the development of the two definitions, you have the same thing in the integrand. So now we take a look at the definition of the area of a surface of revolution. So let y equal f of x have a continuous derivative on the closed interval from a to b. The area S of the surface of revolution formed by revolving the graph of f about a horizontal or vertical axis is given by this. If you have y as a function of x, you have the first formula, or if you have x as a function of y, then you have the second formula. In the first case, r of x is the distance between the graph of f and the axis of revolution. In the second case, r of y is the distance between the graph of f and the axis of revolution. In both of the formulas, you have the constant 2 pi, and you of course have this, which is coming from the definition of arc length. So to further understand this particular definition, let's look at these two diagrams here. We're going to consider the case where y is a function of x. So if you like to revolve your curve, the graph of the function f, about a horizontal axis of revolution, then what is going to be r of x? It is the distance between the graph of f and the axis of revolution. So it is the distance from the axis of revolution to a point on the graph. In other words, it would be the y-coordinate of a point on the curve, which would be given by the rule for the function. On the other hand, if you'd like to revolve it about a vertical axis of revolution, specifically the y-axis, r of x would tell you the distance. Again, what is r of x? Right here. It is the distance between the graph of f and the axis of revolution. But now this would be the distance, because this is the axis of revolution, the y-axis, and that distance is just the x-coordinate of whatever point you have on the graph of f. So here, r of x would be just x. Here, r of x would be f of x. Now we will take a look at two examples to demonstrate this definition. So we're looking at example 6 first, the area of a surface of revolution. It states, find the area of the surface formed by revolving the graph of, our function is f of x is equal to x cubed, and we want to take the graph of f of x is equal to x cubed on the interval from 0 to 1, and we want to revolve that about the x-axis as shown in the figure. So here is our continuous curve. Let me trace it in blue, in red here. Here's our continuous curve from x is equal to 0 to x is equal to 1, and we want to revolve it about the x-axis as shown in the figure. And when you revolve that curve about the x-axis, you get this surface of revolution. So how do we find the area of this surface of revolution? We are going to use the definition of the area of a surface of revolution. So notice that when you look at the solution here, it says the distance between the x-axis and the graph of f is given by r of x. R of x in this definition is telling you the distance from the axis of revolution to a point on the graph. So what is that distance? It is the distance from the axis of revolution, which is being traced in green now, to a point on the graph. So you're talking about this distance, which would be the distance from the x-axis to a point on the graph, or the y-coordinate of that point, which is of course just given by whatever f of x is. F of x is y. So that distance r of x is f of x. So this is going to be replaced by f of x. This is going to be replaced by x cubed. And then of course you need to find the derivative of x cubed, which is 3x squared. And then you're going to replace that for f prime of x, and then you have to square it as well. So that's how you set it up. So you replace r of x with x cubed. The derivative of the function is 3x squared, so you write that in for f prime, and then you have to square it. So 3x squared squared is 9x to the fourth, and then you are taking the square root of that, which is the same as raising to the 1/2 power. So what is it that's being done to go from this line to this line? Integration by substitution. You will let u be equal to 1 plus 9x to the fourth, and you can write the integration by substitution down to help you see that this is in fact correct. And that's how you complete the example. This is example 7 from the textbook. Find the area of the surface formed by revolving the graph of f of x is equal to x squared on the interval from x is equal to 0 to x is equal to square root of 2. But now the axis of revolution is a vertical axis of revolution. It is the y-axis as shown in the figure. So how do we do that? You go back to the definition of the area of a surface of revolution, and we have y as a function of x. We have y is equal to x squared. So we have y as a function of x. So we're in the first row of the definition there. And what is r of x? It is the distance between the graph of f and the axis of revolution. So we have our axis of revolution as the y-axis, and the distance between the y-axis and a point on the graph is given by, in this particular case, this particular point on the graph will have coordinates x, f of x, And the x-coordinate tells you how far this point is from the y-axis. And that's what we need for r of x, the distance between the graph of f and the axis of revolution. So r of x in this problem will be just replaced by x. And of course, we can easily find f prime of x. It is 2x. And you're going to take that and replace f prime of x with 2x, and then you have to square it. So when you do all of that, you replace r of x with x, you replace f prime of x with 2x, and then you have to square it. And the next line will be this. So you have 2x squared, which gives you 4x squared. So you have 1 plus 4x squared, and then you have the square root of that, which is the same as raising to the 1/2. And then you have to do integration by substitution. So if you're not quite understanding everything that's over here, then you need to write down the substitution. And the substitution would be, let u be equal to 1 plus 4x squared, then du will be equal to 8x dx, and then you will continue with the steps for integration by substitution, and that's how you would complete the problem, and you will get this answer. Let's revisit example 6, but change the problem a little bit. So find the area of the surface formed by revolving the graph of f of x is equal to x cubed on the interval from 0 to 1, but this time not about the x-axis. This time about the line y is equal to -2. Or let's make it y is equal to -1. So I can show you on the diagram here. So this would be the new axis of revolution. So we're going to take our curve and revolve it now about this axis of revolution to get a surface of revolution that's going to be different from what you see in the diagram. But how do you adjust the formula? Well, you have the same formula, but remember what r of x is. It is the distance from the axis of revolution to a point on the curve. So if you have this being your new axis of revolution, how do you find the distance from a point on the curve to this axis of revolution? It would be the length of this vertical line segment. The coordinates of the point here will be x comma y. And of course, it's on the graph of f of x is equal to x cubed. So y is x cubed. And this point will have coordinates x comma -1 because this point is on our axis of revolution. And how do you find the length of a vertical line segment? You subtract the y coordinates of the endpoints, top minus bottom. So r of x for our new axis of revolution will be x cubed minus -1, or x cubed plus 1. So that would be the adjustment that we have to make if we change the axis of revolution. We don't want to go ahead and find the surface area, we just want to write the integral for it. So we will write y is equal to 2 pi times the definite integral. The limits of integration are still from 0 to 1 for x. But now r of x will be x cubed plus 1. And then you still have the square root of 1 plus the square of the derivative. So the derivative is the same because we have the same function. So we still have 3x squared. And then you have to square that and dx. And we'll leave it at this because all we wanted to do was write a definite integral that would give us the area of the surface of revolution for our new surface where the axis of revolution is y is equal to -1. I'd like to go ahead and sketch that for you. So here's the axis of revolution, and here's our continuous curve. So let's put that in a different color, maybe green. So what would the surface look like approximately? It would look something like this. So your surface of revolution in this case would be basically the surface that you see here. We will conclude our lesson today by looking at a modified version of example 7, where we will change our axis of revolution from the y-axis to the line x is equal to -1. So now we will have a different axis of revolution, x is equal to -1, which would be right here. So this is our new axis of revolution. So we take our same curve that we had before, but now we will revolve it about our new axis of revolution. So what we have here is from the definition of the area of a surface of revolution. And remember what r of x is. And we're using integration with respect to x because our function, we have y as a function of x. But what would be different now? Well, first of all, the axis of revolution is a vertical axis. But again, what is r of x telling us? It is telling us the distance from the axis of revolution to a point on the curve. So any point on this curve will have coordinates x comma y, but y is given by the function x squared. So we have x comma x squared. And if you want to find the distance from the axis of revolution to a point on the curve, you can draw this horizontal line segment. This point is on the axis of revolution, so x would be -1, and y could be any value. It doesn't matter, but x would be -1. And if you want to find the length of this horizontal line segment, you have to subtract the x coordinates, right minus left. So r of x would be x minus -1. R of x would be x plus 1. So that's the adjustment that you would have to make. So what would you write for the integral? You'd write 2 pi. The limits of integration would still be from x is equal to 0 to x is equal to square root of 2. But now r of x would be x plus 1, the distance from the axis of revolution to a point on the curve. That's r of x. And then you have the square root of 1 plus the square of the derivative. The derivative is 2x, so you still have 2x, and then you have to square that, and then you have dx. And in this particular problem, this is all we wanted to do. We just wanted to write the definite integral without necessarily evaluating it. So today we looked at the development of the definition of the area of a surface of revolution, and we also looked at using the definition of the area of a surface of revolution to find the area of a surface of revolution. And we also looked at a couple of examples where the axis of revolution is a vertical axis or a horizontal axis other than the y and the x axes.